That's fine by me.
Good morning, everyone. Welcome to this week's IQS seminar. We have, for this week, we have Gerwin Koolstra from EeroQ Quantum Hardware. Gerwin, he did his PhD from University of Chicago in Sister's Lab, and he was a postdoc in Irfan Siddiqui's group in UC Berkeley. Today, he'll be talking to us about his work on discovering the quantum properties of a single electron floating on liquid helium. Gerwin, the floor is yours.
Thank you so much. Yeah, thank you for the invitation to give a colloquium. It's really fun to talk about science. I don't get to do that as much as I like anymore. So any opportunity, I welcome that. And so thank you for the invite. Yeah, so today I'm going to talk a little bit about relatively old and also new quantum system, namely electrons, liquid helium. And the first time that I personally got in touch with this system was when I started to look around for who I wanted to do my grad school with. And this was more than a decade ago now, in 2013. And I walked to the door with my soon-to-be professor, David Schuster, and he started telling me about the possible projects. And at the time, I was actually convinced to do grad school with someone else at Chicago. And as soon as he started telling me about this particular project that he had in mind, namely making quantum bits on superfluid helium, I was so mesmerized by the idea about it. And I was thinking, oh, why are not many more people working on this project? And I just thought, okay, I have to do this. This sounds so amazing. I need to work on this for my grad school. And the rest is history. 10 years later, I'm basically still working on it. So I hope that in the next 30, 45 minutes to an hour, I hope to convince you how magical this system is and how much fun it is to play around with electrons that are floating on liquid helium. So I work for a startup called EeroQ, and we're based in Chicago. And the goal of that startup is to make a quantum computer out of these single electrons floating on liquid helium. And so let's start with, okay, how does this system actually work? And to explain it, I just need two basic simple ingredients, namely one electron, and two, I need the liquid helium. And imagine now that you have some power to control the electron. And if I took this electron and I put it near liquid helium, what would happen is that the electron, it would slightly polarize the liquid helium and induce an image charge inside the liquid helium. And if the helium were a metal, that image charge would be exactly the opposite charge. But because it's a weak dielectric and the polarizability is a little bit weak, actually you get an image charge that's about 3% of the electron inside the helium. And that image charge, it exerts a pulling force on the electron, and so it binds the electron to the helium. But it's not so strong that electron gets pulled through the helium. And that's because the helium actually has a 1 electron volt barrier for the electron to enter in the helium. And the reason for that is if you go back to your quantum mechanics class, helium has 2 electrons in its outer shell. And so I cannot put an extra electron in there because that would violate the Pauli exclusion principle. And so that results in that 1 electron volt barrier for the electron to push through the helium. And so what ends up happening is that, this system where you have a negatively charged electron that's then bound to a slightly positively charged image charge kind of looks like a hydrogen atom, where the proton, in this case, is just replaced by the image charge of the electron. And, basic quantum mechanics, you can draw what the potential looks like for this electron. And that's sort of shown over here. And you can then solve the eigenstates, which are shown as these psi's over here. And basically what this means is that the ground state energy of the electron results of being that the electron is about 10 nanometers above the helium. And this is the competition between that pulling force of the electron and the 1 eV barrier for the electron to go into the helium. And so the next nearest excited state, which is about 30 nanometers higher, is about 120 gigahertz away, or 5 Kelvin, choose your favorite units. And this actually means that in experiments, we don't care even as much about these excited state, because for typical experimental temperatures where we operate at 10 millikelvin, the electrons will always be in its vertical ground state. So they'll always be floating about 10 nanometers above the helium. And while this all flows from basic principles of like electrostatics and quantum mechanics, I think this is just the most magical thing, that just you take an electron, you put it on helium, and it just floats 10 nanometers above the helium. And so if we have this electron now that's floating 10 nanometers above the helium, we can in principle just move it around, because the helium is free of bumps and impurities. And so the electrons, can move around with record high mobilities, which has been shown over the past decades that there's some amazing transport properties of these electrons. But if we want to, for example, to study it, we can confine these electrons just with DC electrodes that are either in the same plane as the electrons or just below the helium. So this allows us to, for example, to measure electrons, but also to control them and to suck them from different places. And also we'll use this property to develop qubits later. Okay, so this system has been studied for quite a while, actually. It was first discovered in the 1960s by Soviet physicists and also people in the US. And over the decades, actually, it's been like a really interesting playground for many-body physics. Because one thing that's very interesting that happens with these electrons is that if you decrease the temperature far enough below 1 Kelvin, these electrons, they actually crystallize into a state called the Wigner crystal. And this is one of the few systems that's clean enough where you can actually see the effects of this crystallization happen. And that has led to experiments where, for example, where people have squeezed and reduced the dimensions of these Wigner crystals from 3D to 2D, sorry, not 3D, but from 2D to quasi 1D geometries. And that gives all kind of interesting physics. But since the 2000s, people have also more focused in the system on developing quantum computing and thinking about quantum computing. There have been several proposals for different types of qubits, which I'll talk a little bit more in next 2 slides. And so experiments have focused on singling out single electrons from these many-body electron states, and then also focused on for example, shuttling electrons across CCD chips, which was done, for example, in Princeton here in 2011. And so at this point, you might wonder, okay, why would we do this? What is the advantage of electrons on a helium? And I thought I'd kind of summarize this a little bit. And please keep in mind, I'm not in any way trying to sell a particular architecture, but this is a slide sort of to convey like what do people think about as the positive aspects of electrons and helium. And for example, these electrons and helium, they share many benefits of 2 particular architectures. And I think they're sort of, you can think of them sort of like a mix between ions and semiconductor qubits. And for example, in ions, all the ions are in principle identical. And for electrons and helium, at least the spin state, that is true as well. You can shuttle ions across the chip as you can with electrons, and they're compatible with the CCD architecture, which is usually beneficial for scaling down the road if you want to make a scalable quantum computing architecture. Except that for electrons and helium, we don't need lasers, for example. So we just use DC voltages to shuttle these electrons around, which is immensely helpful. Also, they look a little bit like semiconductor qubits, because with semiconductor qubits, there's a 2D electron gas, typically confined in this heterostructure well. And for electrons and helium, that's the same type of gas. I'm putting gas in quotation because you saw that in the last slide, I was arguing that it's more like a crystal. But this system exists on the interface as a 2D system. For electrons and helium, it's again, on the vacuum and the helium interface. And as I said, just like semiconductor qubits, these electrons, they can be transported and measured with DC voltages in principle. But for electron helium, it's nice because the helium is atomically smooth and in principle has no impurities. The only impurity being helium-3 potentially, and that can be filtered out with isotopic purification. Okay, so as I said, there were many proposals since the year 2000 that explored electrons and helium as quantum computing qubits. And here I'm going to list 3 of them, the 3 most popular variants, so to say. And actually, one of them I already told you about, which is the vertical motion of an electron and helium. And this is just to say that here I'm drawing again the potential seen by the electron and helium which includes the potential barrier of the helium, as well as the attractions to its image charge. And in principle, you can make a qubit out of those states as well. The problem is that, as I said, those frequencies for the transition frequencies tend to be in the hundreds of gigahertz range, which is slightly difficult to work with as an experimentalist. And also, people have shown that the coherence of these states tends to be roughly a microsecond or so. So it's not the best qubit, so to say. On the other hand, there's the spin qubit, which in some ways is almost the perfect qubit because you only have two levels. If you apply a B field, the spin up and spin down transitions, or spin up and spin down levels, they split according to the Zeeman splitting. And in principle, there's only 2 levels there. You don't have to worry about secondary levels. And if you have many qubits, many electron spins, they would all split according to the same B field. And so while this is almost the perfect qubit because there's 2 levels, the coherence times are expected to be very, very long. It's also extremely difficult to measure because the spin state is so isolated. So the problem here for the spin state is really the measurement. How do we tackle that? And then sort of in between is this in-plane motion, or the charge state for electrons and helium, which is really the motion of the electron that's parallel to the surface of the helium, which can be controlled by the electrostatic potential, shown in gray here. And that can in turn be controlled by, for example, by electrostatic voltages that are either due to electrodes below the liquid helium or in the plane of liquid helium. And this was a proposal that was put forth by David Schuster in 2010 to make a qubit out of this motional state. And he showed that, considering the main processes for decay, dephasing, and so on, he would predict that the coherence time of this motional state would be about 100 microseconds. And not only that, but if we were able to make this into a qubit, then by additionally applying a gradient of the magnetic field, one could use this motional state as a gateway to the spin state. So that's extremely valuable. So that's why in this talk, I'm going to focus on how to make a qubit out of the in-plane motion state of an electron and helium. Okay. The first thing to do when you make a qubit is to think of a way to read it out. And that's typically been the hardest part for electrons and helium, because typically people have resorted to, what people call Summer-Tanner techniques, which are essentially huge capacitors, which you can put voltages on and slightly alternating voltages to transfer electrons that float on top of these capacitors and then induce charges on these other capacitors, and that induced charges then converted to a voltage and read out. The problem with that technique is that it's existed for 70 years and it's been perfected in principle, but people have never really managed to measure small number of electrons with it, because that technique is at low frequencies. There's a lot of experimental noise. It's just not sensitive enough. And the solution that during my PhD that Professor Schuster and we worked on is to use circuit QED to couple the field of a microwave resonator, here shown in as the field going from the right or the left red pin to the right negative pin to the electron that's floating on top of the helium. And in principle, that should work well, but let's take a step back and think about what circuit QED is, because I'm sure that some in the room are familiar with that, but maybe some are not quite so familiar. So circuit QED is essentially a technique that allows you to couple a two-level system or a multi-level system to the bosonic degrees of a cavity. And there's three important parameters in this system, which is, first of all, the coupling strength G, that determines how quickly does energy swap from the two-level system to the cavity. There's the cavity decay rate, which says that if I store some photons in this cavity, how quickly do the photons leak out? And then lastly, there's the orbital decoherence rate, gamma, which says that if I have an excitation in my two-level system or multi-level system, how quickly does that leak out of the cavity and result to a decay or dephasing process of the qubit. And the holy grail of this system has always been to achieve those strong coupling regime, where the coupling strength is larger than both the cavity decay rate and this orbital decoherence rate, kappa and gamma. And this actually resulted in a massive progress back in 2004, which was the result where for superconducting qubits, where a single photon was coupled to a superconducting qubit. And since then, a lot of different quantum effects have been explored in that system, and we hope to do the same in this system for electrons and helium. Okay, you say, okay, well, how do we do that? So if we write out what the coupling strength is in terms of the dipole moment of the electron and the electric field of a microwave resonator, you can write out and see that it scales, partly due to the dot design. And so if you have an electron and you want to confine the electric field as much as possible, make it very strong, that will increase the coupling strength to your electron. There's also a part that is due to the 0-point fluctuation of the electrons. So if I have an electron that fluctuates normally a lot, that gives me a large coupling. And then lastly, there's a part that is due to the resonator design. And these are the 0-point fluctuation of the mode. So the voltage that's essentially across a capacitor where you put the electron in. So if I maximize each of these points, I should be able to get to strong coupling in principle. And, G, typically when you do the calculation, your naive estimates would be saying that G should be roughly in the order of 1 megahertz. And that would allow you to, in principle, do much faster readout than these previous techniques, which were based on slow kilohertz sensing techniques. And if you have a megahertz, you should be able to do fast and sensitive readout in about a microsecond, which is a huge improvement. And this has been done in many other systems. So we're not the first ones to try this for our hybrid quantum system. For example, in silicon germanium quantum dots, gallium arsenide quantum dots have done this, and also more recently, a project that I was also involved in, we've shown that electrons floating on solid neon can also reach this strong coupling regime. Okay, so during the work that I did during my grad school, we made a big step to actually achieving this strong coupling regime and accessing the quantum effects of electrons on helium. And I'd like to briefly walk you through that experiment. I'm going to skip a whole bunch of steps, but feel free to interrupt me if that's unclear in any way. So what you see here is a picture of the device that we fabricated. And in particular here, you can see the microwave resonator which is on the bottom of a microchannel. And during the experiment, the microchannel is actually filled with liquid helium. I just didn't have a picture. I can't take a picture of that, of course. So you have to believe me that in the experiment, this trench here is filled with liquid helium. And also there's electrons that are floating on top of the microwave resonator. And And the tip of this resonator here, you see that there's a little island. And this island is what we call a quantum dot for electrons and helium. It's about 8 microns wide, so much bigger than maybe the semiconductor quantum dots that you're used to. And on the side here, you see several guard electrodes that would allow, to us to transport electrons from the reservoir that's sitting on top of the microwave resonator, and then pop them one by one, or pop them basically into this dot. And that was a difficult experiment to figure out how it's working, but eventually we were able to do that. And I haven't talked about this green electrode here. This green electrode is actually very important. The green electrode allows you to control the electrostatic potential here shown in black. And in more precisely, the curvature of that electrostatic potential is directly going to affect the electron frequency. And so the idea was that if this electron frequency equals the resonance frequency of that microwave resonator, we should see a big signal as we look at the output of our microwave resonator. And that's the measurement I'm going to show you just now, is that I'm going to monitor the resonance frequency of our resonator as here in vertical slices in the color. And, in principle, when we're far away, not much happens. But then for some voltage, this is the trap voltage, which controls this curvature of the electron frequency. And for some particular voltage, you see that the resonance completely disappears. And for this particular voltage, the electron frequency is indeed quite close to the resonance frequency, and actually it crosses at that point. And this is confirmed by modeling, which we did using analysis of the electrostatic potential that's generated by all these electrodes, and it works quite well. You see that in particular, in this device, the resonance frequency was around 6.5, and when the voltage is set to that value, you see that there's a sort of an upswing in the frequency shift, a downswing, which indicates that there's a crossing between the electron and the resonator. Okay, not only that, but now we can actually infer some properties, some circuit QED properties from this particular data. And the first is actually the resonator line width, which was the rate at which photons leak out of the cavity. This is relatively easy to infer. You can go off resonance and you see that it's about 0.5 megahertz. And then from the modeling that we did, these fits in these lines, we can infer that the coupling strength in that experiment was around 5 megahertz. And then finally, the last parameter here was basically the decay rate, this orbital decoherence mechanism, which was in fact the largest, and it was around 80 megahertz. And so this is that means that for this particular experiment, the system was not in the strong coupling regime, because the condition G larger than gamma and kappa was not obtained, essentially. And at the time, we thought that the reason for that was that the low frequency helium vibrations were messing up the electron properties. And so you can think of this because helium is a superfluid, and we could directly see in our resonance spectrum that the helium was essentially bouncing up and down based on building vibrations, based on the vibrations from the fridge that we had. And this was an immense problem that we thought and hoped to solve during my time at EeroQ. And so I'll talk to you a little bit more about that later in the presentation. Okay, so here's what I'm going to talk to you about today. So the question is, how do we go from what we had in 2019? How do we go to the strong coupling regime where we think that we can achieve all of these amazing quantum experiments? How are we going to achieve that? Going from 1/16 to 1, this ratio, G over gamma, seems like a rather daunting task. But what I'll hopefully show you today is that by increasing some resonator properties, we can actually make a big step towards that. And then finally, in the end of my talk, I'm also going to show you how we can reduce this decoherence gamma also to boost maybe this ratio G over gamma. Okay, so let's get started on point number 1. So for this, we need to go back to the definition of the coupling strength. Again, if I write this out as h bar g is the dipole moment of the electron times the electric field of the microwave resonator. Again, there's a dot geometry part, the 0-point motion of the electron itself, and then there's the resonator geometry. And here we're going to really focus on this last part, which is the 0-point fluctuations of the voltage of that mode that is across this capacitor C here. And I can write that as the resonance frequency of my circuit times the square root of the resonator impedance. And so this means that if I want to increase G, I need to increase the 0-point fluctuations, which means that I need to increase the impedance of my device. Okay, then you say, okay, how do I do that? Well, the impedance is basically the square root of inductance of my resonator divided by the capacitance. And so, fair enough, if we want a large Z, we want to minimize the capacitance and increase the inductance. Okay, then if I think about, how do I make a resonator that works like that, then you can imagine, for example, the simplest model for a resonator is a coplanar waveguide resonator that we're in superconducting qubits that we're very familiar with. And in order to make the capacitance really small, I should just increase the gap. That's easy. But it turns out I also need a big L. And for most superconductors, the L is essentially limited by the magnetic permeability. And so this limits the impedance for most regular superconductors to about 300 ohms or so. So that's very difficult to make a high impedance resonator this way. So instead, we came up with an idea to use kinetic inductance of a superconductor to boost this inductance even further. And if you're not quite familiar, let me just explain and give a brief tour of kinetic inductance. So kinetic inductance is essentially the kinetic energy that originates from the Cooper pairs that travel in a superconductor. So imagine you can think of this center pin of the superconductor CPW as a wire that has some cross-sectional area A. It has some charge carriers, which in superconductor are Cooper pairs, and they move at some velocity v. And it turns out that I can write the kinetic energy as I squared with a prefactor that looks a lot like an inductance. And if I write down the inductance in terms of this number density, for example, of Cooper pairs, the charge of the Cooper pair, and also the mass, then you find that there's the inductance scales as something that depends on material properties, this mass, the N and the E, but then also something that depends on the geometry. So for example, this means that I can either increase this kinetic inductance by finding a particular material that is really high kinetic inductance naturally, or I can shrink down the area, cross-sectional area of my device such that also this value blows up. And turns out we basically do both. There's several materials that are really good for kinetic inductance. One of them is, for example, titanium nitride. That's personally my favorite. And then also we make the films that we use, make them really thin. And so this results in, for example, these resonators we've tried during my grad school career. We showed that these work really well. They're very thin. They have very high impedances up to larger than the resistance quantum can be even. And yeah, they still have high Q, which is great. But if you look at these resonators, they're not really conducive to coupling to electrons. And so the question is now, can we come up with a design that's tailored to electrons and helium? And the question is, of course, yes. So we recently published a paper about this. Link is in a couple of slides. But the idea here is that in order to come up with a better resonator design that's coupled strongly to electrons and helium, we can start with this simple LC circuit that I showed you a couple of slides ago. And then take a copy of that and then couple these individual halves with a capacitor. And that's essentially what we call this symmetrically coupled resonator. You see that there's two copies of a resonator, of the LC lumped element resonator on left and right side. And a capacitor here where we intend to store the electron and couple the electron. So this would be the dot area, essentially, that I showed you a couple slides ago. Now, okay, what's the trick here? So the upshot is that you get a large coupling strength, which is, increases by a factor of square root 2, which is great. But this comes at a price, and the price is that, you have one extra mode to deal with. And if you diagonalize the Hamiltonian of this circuit, you see that you get two circuits, or two modes, sorry, in this circuit. One is the sort of what we call a common mode, where the voltage on A and B oscillates in phase. And the other mode is a differential mode, where which has the opposite mode, where the voltage oscillates out of phase. And it turns out that for an electron and helium, we want this mode to couple to the electron, because this mode doesn't couple at all. So in principle, this extra mode doesn't hurt us at all. We just need the differential mode. And if we look at just the differential mode, we get this square root 2 enhancement of the coupling compared with a simple LC circuit, which is great. And so we wanted to understand a little bit better and verify that we weren't tricking ourselves. And so we wrote down the theory in the classical limit, I should say, for this circuit, including some electrons that in the dot, and we even included the possibility of there are more electrons. So we wrote down the kinetic energy for the electrons, the electrostatic potential, as well as the pairwise repulsion of the Coulomb force. And then finally, also including the Hamiltonian for the coupling to the resonator, which is essentially just saying like E times the voltage on this node is the coupling. And that, if you expand it out to linear order, you get that it basically, the differential mode couples to the electric field EX, and that's still the case. So if you really are into the theory, I encourage you to solve these equations. But if not, I also wrote a nice diagonalization script that you can do this numerically. And the results of that, you can look at the GitHub. But the results of that, if you believe me, then you can also look at this figure. And they essentially show that if let's say I have one electron in a dot, and I vary the curvature of my electrostatic potential, which would be the second derivative of this one, when that curvature equals the resonance frequency of the differential mode, that differential mode is going to show a strong coupling to that electron. On the other hand, the common mode, which has the voltages oscillate in tandem, does not show any signature of coupling at all. So this is essentially as what we expected. And for the values that we thought we could make, these LNCs, you see that the G is roughly on the order of 40 megahertz or so. So this would put us much, much closer to the strong coupling regime using these circuits. And so we decided to make a couple of these as a test. And here you see an image of such a chip. And so there's 9 resonators of this style, which have sort of like this symmetrically coupled design with a capacitor in the middle, where we would put dot infrastructure there, but currently these were just some test resonators. And we show that these Qs are actually really good. The internal Qs are upwards of 400,000, which is more than enough, at least to reach the strong coupling regime. But there's one other thing that we need to check, for example, which is the impedance of these devices. And the impedance, that's a little bit harder to analyze, but we're able to do it nonetheless. And you can see that there's the impedance is roughly 2.6 kilo ohms, and which would then predict 5 times enhancement of the coupling strength to electrons and helium. So this is to say that swapping this material with tin nitride really boosts the impedance of these resonators, and this is immensely valuable for coupling to electrons and helium. And I should say, if this number means nothing to you, typical coplanar waveguide resonator made out of aluminum, niobium, is roughly 50 ohms. And so that's where if you divide this number by 50, take the square root of it, you get roughly a 5 times expected G enhancement. But we need to show that this is actually true. And so the next step is to take this resonator design, put the full dot infrastructure there, and start doing experiments with electrons and helium. That's what we're all here for in principle. Okay, so let me transition into that. Okay, so here you see a new device that we made in the last year that has this resonator design, which has these symmetrically coupled halves. And the tips of these resonators then arrive at an area where there's a lot of other electrodes, and the blow up of that is shown over here. So you can see the resonator pins coming in. There's an area here where, again, we have a quantum dot for electrons and helium. And there's a trench. Trench is about 0.7 microns deep. It's 3 microns wide. And on the bottom of that trench, there's a trap electrode. And again, if you remember from the previous data, that trap electrode really serves as to change the curvature of the electrostatic potential for electrons that float in this dot over here. And as they're in the dot, the resonator will couple to the electric field of the resonator will couple to these electrons, and we should be able to see all kinds of interesting effects of these electrons. And so to summarize that, there's a trap electrode. A trap electrode controls the electrons that are floating in the channel here, but it also, since it extends into the dot, it controls the frequency of electrons that are floating in the dot. There's the trap guard electrodes, which control how many electrons do we let from the trap channel into the dot. There's the unload electrode, which pushes electrons out of the dot. And then finally, there's this resonator bias, which we can also control the curvature of the electrons that the electron sees as well. Okay. So now I'm going to show you how we typically detect these electrons in our experiment. So the experiment that we do starts with spraying some electrons from a filament. So we run a current through a filament, and that basically allows us to catch these electrons on top of the trap channel, but nothing is in the dot yet. And so the next thing we do is to open the trap guards, essentially, or lower the barrier, and that would allow electrons from the channel to go into the dot. And we see that over here. If we make the trap guards here slightly more positive, the electrons go from the channel into the trap guard, or into the dot over here. Okay, and that's accompanied by a large frequency shift, as you can see, of about 100 kilohertz. And our FEM indicates that at this particular point, we have about 20 electrons in the dot. And this FEM potential, you can also see it here, and that indicates that electron transport is actually happening. And we can find out what the chemical potential was on top of the trap electrode. And we can find control over that. For example, we can lower the trap voltage a little bit, and that allows us actually to control the chemical potential in this trap area for the reservoir. So a very good control over the loading procedure. But then our goal is to reach one electron. And that one electron, we do that by using this purple electrode. And the strategy here is kind of important because it's very hard to load just one electron. It's much easier to load, let's say, 20 and then kick them out one by one. And so we do that by first loading, let's say, 20, and then successively unloading a little bit more, and then returning to the probe condition. And this allows us to really figure out how many electrons are left in a dot each time we unload a little by little. And that's procedure should only change the number of electrons. And so the next experiment I'll show you really shows that experiment. So again, on the y-axis, I'm plotting the frequency of our resonator, so which is only sensitive to things around the dot, in the dot. And if I start with not as much of a negative unload voltage, you can see that it starts off kind of flat, but then I see some step-like features appear in the data all the way until there's no more frequency shift left. Okay, so you might say, okay, maybe there's some steps, but how can you really be sure that the data is kind of noisy? And one way to tackle that tackle that problem is for each of these points to also vary the curvature of your trap. And if I do that, I can make these steps a lot more visible. So that data is shown on the right. This is essentially on the x-axis. I'm plotting again the unload voltage, which is supposed to reduce the number of electrons in my dot. But then also in terms of on the y-axis, I'm changing this curvature of the electrostatic potential. And what you see is a lot of discrete changes in each of these at particular voltages. And if I take the dashed lines where these changes occur and I plot them on top of the left plot, you see that, now all of a sudden these steps are becoming a lot more clear. And now you can say, okay, I know that at the end, I know I shouldn't have any electrons available in my dot anymore because the frequency shift is truly zero. And that means that this is probably 1 electron, 2, 3, 4, and we see up to 9 electrons in this dot, which is really kind of cool. We have a lot of discerning power. Okay, so I want to come back to this plot for a second because there's so much information there, which is really cool. I don't have time to go all the way into it, but one particular interesting feature is, for example, if you have 9 electrons, you can imagine a situation like this, which is you have 9 electrons trapped in a dot, and you might wonder, like, what mode of these 9 electrons is actually coupling strongest to my differential mode of the tinitride resonator. And this is exactly why I wrote this package, again, Quantum Electron. And if you're interested, please check it out. It's incredibly fun. That's how I made these animations. Incredibly fun to play with. For example, yeah, there's these 3 electrons that exhibit 3 different modes, of course. And for this particular potential, this is the most strongly coupled potential. But for now, okay, let's focus just on the n=1 state. And yeah, I'd like to show you, after some tune-up of the voltages, what that particular crossing actually looks like. And here I'm showing the data where I'm monitoring the resonance frequency of a resonator again, and I'm sweeping the frequency again of this electrostatic potential. And when I do this, you see 2 features appear, one on the right and one on the left. And when I simulate these electrostatic potentials, what I would expect, you see that you transition on the right, where you have a single well at some point, and then you eventually have to end up on the left with a double well, which is the potential here simulated on the left side. And so what happens, we think, for this particular picture, is that we start off with an electron that's in the center of the dot. We lower its curvature, and eventually that curvature crosses the resonance frequency at particularly this point. Then there's a region where the potential is extremely flat. So the frequency of the electron that's oscillating in that potential essentially goes to 0. And that's exactly in the center. And then finally, we see something come up again. And that's where the frequency of that electron actually oscillates in one of these lower or the upper well, depending on if there's some experimental flaws that break that asymmetry. It might oscillate either left or right. And so to analyze this data, again, we can fit the resonances, and we see that there's some shifts down, shifts up, and now we want to figure out what our circuit QED parameters are. And what we find is that if you just look at this data, it's actually not so trivial to figure out what your circuit QED parameters are, and that's because these G and gamma, they're kind of linked. It's hard to independently extract these G and gamma from these data. But if we assume for a second that our G was intended as from design, which was in this case is about 100 megahertz, then again, we find that in this particular case, a gamma of 100 megahertz would fit the data reasonably well. So that means that for this particular data at this point in time, we're very much on the threshold of strong coupling. And the way to prove that essentially is to go on resonance and look at the double peak splitting, a hallmark of strong coupling regime. Or we can do this with Qubit spectroscopy, which is a technique that people often use in superconducting qubits, where they have a second tone, sweep it over the qubit frequency and look for changes around the resonance. And this would actually give you a lot more information, for example, like G, about gamma, and also about enharmonicity of this particular state, which is, of course, something I haven't talked about, but is incredibly important when you want to make a qubit. Okay. I want to talk maybe last couple minutes about our possibility of decreasing the dephasing rate gamma. And that's actually, as you might expect, it's a lot more tricky of a problem as it is, with any system to find out lossy sources, and that tends to become quite tricky. But one thing that we quickly realized is that actually with the most advanced vibration isolation technology that we have at EeroQ, we didn't see any difference whether we reduce those vibrations or whether we turn all the vibrations basically off. There's no difference. And this means that we conclude that these classical low frequency helium vibrations, which we first concluded were the biggest problem, actually don't affect the line width of our system very much. And this is actually a big mystery until we started to sweep the temperature of our system. And so what we saw there was that starting from the base temperature, we slowly start to increase the heat to the mixing chamber, and things started to look radically different, so as you can see. And the extracted line width that we saw actually closely follows the square root of the temperature dependence, which is something that I think in superconducting qubits is not so well known. I think the closest thing I've seen is in, for example, in ion traps. It's kind of I've seen something like that where the voltage noise from electrodes can look a little bit like a square root of T dependence. But we talked to a theorist, and he had actually looked into this problem before, and he figured out that this could be a sign of helium surface fluctuations coupling to the electron. And if you go into this paper, I'll link it over here, you'll see that the line width that's produced by this phenomenon would scale with a square root of T. There's also a factor that has the surface tension of the helium in it, as you might imagine, that becomes important. And I guess the saving grace in this experiment is that, or in this particular expression, is that it has a perpendicular E field that enters, and it scales linearly with that, which means that in principle, if we are able to reduce the holding field, essentially the coupling of this electron to the surface waves, if we can reduce that, then there's a way for us to reduce the line width of electrons in helium. Okay, so that brings me to my conclusion. So I hope that today I've convinced you that electrons and helium is a really clean system with potentials for quantum computing. Also that once we get to the strong coupling regime, that this motional state would unlock a lot of cool quantum experiments, and we're actually almost there. I put the red dot very close to G over gamma as 1, but not quite there. And that was basically possible but through this engineering of these high kinetic inductance resonators, and potentially more improvements in gamma, which put us over the edge to the regime where G over gamma is confidently larger than 1. That's the goal. And I'd like to also quickly flash the other work that's going on at EeroQ. So we're working on this one, but at the same time, we're also working on showing that these techniques that I've showed over here, that those are all possible at higher temperatures as well, which is extremely cool. And this is, for example, a single electron unloading curve that was done at 1 Kelvin. And then also separately, we have a scaling aspect where we try to, we order chips from a semiconductor manufacturer and, try to process those to also do electron experiments on those, which is important for the scaling of quantum chips. And with that, I'd like to thank you for your attention. I welcome any questions. And this is the EeroQ team.
Thank you very much, Gerwin, for such a nice talk. Time for questions. Questions?
When you were mostly focused, Gerwin, you were mostly focused on the single qubit functionality. Have you thought a little bit more about interacting them, making 2 qubit gates and this kind of thing?
Yes, so there's different, I think the company is mostly focused on spin qubits. So I guess the idea would be to eventually come up with, use this motional state to address the spin state, and then work with, 2 spin qubit gates to build quantum computer. There are some proposals that are out there to use the charge state, like what I've been showing you today. And one can do that either through the interaction of a bus. So let's say a resonator, you can couple 2 electrons with a resonator to each other. The problem with that is that you're limited in the Q, or your gate fidelity will be limited by the Q of the resonators in between. That's kind of a weak point of that strategy. But there's also a strategy where you can think like, okay, let's assume that I have 1 dot, and then I trap 2 electrons in that dot, and I can, maybe through the Coulomb interaction, I can have these electrons interact and get some entanglement that way. And that's been explored before. There's theory proposals out there, and there's ways that you can do, I think, a CZ gate that way. The problem is that the Coulomb potential, if you want to explore that, the Coulomb potential is long range, as you know. And so it's hard to turn that interaction off unless you physically move it really quick, very far away. So that ends up giving you, I think, static, whether it's a ZZ term, I think that, or ZI term, I forget, in the Hamiltonian of your gate. So there are some issues with that. But in principle, if you worry about the spin state, then it becomes a lot easier to work with that. Did that answer your question? I hope so.
I had a question on what you were expecting on the readout time and readout fidelity when you have this improvement, when you, let's say, get the strong coupling that you're looking for. What are you expecting for readout quality?
It's a good question. So I guess the metric of readout fidelity depends on a lot of things. So it depends on, let's say, the readout, it depends on basically G, kappa, and gamma, as well as, well, I guess T1 and T2 times as well. So ideally, if those decay processes wouldn't matter, then I would think that, it's just set by, let's say, and also there's of course, the qubit frequency where you position it, that would also come into play. So it's really hard to say. I think since this looks a lot like superconducting qubit readout, one might expect that you're going to be limited by some 99% fidelity readout. But of course, their qubits are much higher fidelity, and they're maybe 10, 20 years ahead in terms of electrons and helium. So there's a little bit of a question in terms of speed. I think, yeah, it's possible that the speed of the readout is going to look exactly the same, because once you get your G to 100 megahertz, which is what we've shown, electrons and helium, or that G is very similar to electrons or superconducting qubits. And so I don't see a reason why it would be different at all. So yeah, it's possible that 99% level is also possible in electrons and helium, but probably requires, first of all, more understanding of the system, and then, a lot of engineering to get it stable and get the parameters in a better range.
Thank you. Any question over Zoom? Not, let's thank
Gerwin again.